My name's Bill Moore. As Chris just said, I'm a planetary geodynamicist with interest in a wide range of processes, but in particular, how the interiors of planets interact over long periods of time with their surfaces and atmospheres to produce the kinds of environments that we see. But I wanted to start doing this right. I'm not. There we go. Got it. Okay. First off, I wanted to introduce Hampton University to you all because most of you are probably not familiar with us. We're one of the nation's premier historically Black colleges and universities, founded in 1868 as the Hampton Normal School and Agricultural Institute. Actually, those are pre-COVID numbers. We're down to about 3,500 undergrads, but we're looking to grow back up post-COVID. And I wanted to introduce the Atmospheric and Planetary Sciences Department to you. So planetary science at Hampton University is currently me. We do have an opening, faculty opening, should have been announced last week, I think, or maybe it's coming open this week. So if any of you know any young scientists looking for a tenure track job in planetary science, please send them our way. We are interested in planetary atmospheres, planetary interiors and dynamics, mission concept studies, habitability, and astrobiology. In atmospheric science, we have very strong program in remote sensing and various other aspects of atmospheric data collection, data analysis, and severe weather forecasting. We also happen to have a faculty opening in severe weather climatology as well. So if you know anybody interested in that sort of job, please send them our way. In the Atmospheric and Planetary Sciences Department, we are a graduate-only program. We offer masters and PhDs in both atmospheric and planetary science. So any undergrads interested in grad school, please keep us in mind. Okay, so now we'll get to the talk about Venus and Earth. There are basically two flavors of planetary tectonics. There are planets where the lid does not move. It's essentially one solid shell. And there is a planet where the lid does move, and that's the Earth. We refer to it here as mobile lid, but of course we generally talk about it as plate tectonics. And this remains an outstanding and very fundamental question in planetary geodynamics. Why do we have these two flavors? Well, if you just think about it from the standpoint of what rocks do and what they're made of, we have a thick shell of cold material at the top, which we call the lithosphere, which is also the part of the Earth where heat is being conducted from the interior, which is able to move and convect, through to the surface. And because we have a very strong material property dependence of rocks on temperature, we end up with cold and very stiff rocks up here at the shell, and that's the lithosphere. Typically, the heat that can be conducted through the lithosphere, you can think of as scaled by conductivity times delta T over D, where D is the thickness. And so if we know a certain change in temperature between the surface and the interior, then we can estimate how much heat flow is able to get through the lithosphere. And it's inversely dependent on the thickness of the lithosphere. So if the lithosphere gets thicker, we can conduct less heat. If the lithosphere gets thinner, we can conduct more heat. And so when we have high heat flow, it implies a thin lithosphere or a hot interior or both. There we go. And so we can do some idealized kinds of numerical simulations. These are two-dimensional convection simulations. We put in the equation, the Navier-Stokes equation, well, actually the Stokes equation that governs mantle flow. We put in a temperature equation. We couple them and run them forward in time. This actually includes the very strong temperature dependence of viscosity. And we see, sure enough, you get a thick, strong lid here. These red colors are a very high viscosity, strong lid that doesn't participate in convection. And in fact, that is where conduction is happening through the lid. And you can see this would be the geotherm of these various planets. And what's different here is we're changing the ability or the ease with which that planet is able to transport heat convectively, governed here by the Rayleigh number. And so as the Rayleigh number goes up, typically we would think of this as the viscosity going down. The material is able to flow more easily, more rapidly, and transfer more heat with less temperature difference. So you'll notice that as the Rayleigh number increases, the internal temperature actually decreases. All of these models are transporting exactly the same amount of heat, but they're doing it through the lid at different temperatures. So we ordinarily think of the thickness of the lithosphere as being governed by the amount of heat that needs to get out of the interior. And so early on in the planet's history, when there's a lot more heat that needs to get out, we would expect a thin lid. If we look at terrestrial planets, they should at the beginning have been 5 to 8 times more heat being produced. This is because radioactive decay has gradually removed those heat sources to today. So if we roll back several half-lives to the beginning of planets, we end up with between 5 and 8 times the amount of heat that needs to get out, and therefore between 5 and 8 times thinner lithospheres. Okay, in order to get this heat out of those early planets, they must have had rather thin lithospheres. But this becomes a problem, because when we look at the other terrestrial planets, we find ancient topography preserved to the present. So this is the map of Mars's topography. You see that the southern hemisphere is high in red and yellow colors. The northern hemisphere is low in blue. And there's a rather sharp change right along here at the green-blue boundary, which is known as the Martian crustal dichotomy. There are a couple of kilometers of topography between here and here, and those couple of kilometers of topography have not relaxed. They are being held up by elastic forces in the Martian lithosphere. And they have been held up by elastic forces in the Martian lithosphere for more than 4 billion years. Based on crater counts, including craters that are buried underneath the lava plains in the northern hemisphere, the Martian crustal dichotomy is at least 4 billion years old, and it hasn't gone anywhere. If the lithosphere were really 5 to 8 times thinner back then, we would not have expected it to be able to support this topography, certainly not for this long. Let's look at the moon. The moon is a synchronous rotator. It is subject to rotational flattening. It is also subject to the permanent tide from the Earth. The permanent tide from the Earth is trying to pull it into kind of a football shape, and the flattening is trying to squash it along the poles. Because it's a synchronous rotator, the ratio between those tidal forces and the rotational forces is fixed. And it turns out if you write the potential that includes the tidal potential and the rotational potential, you'll see that they depend on the distance of, or the period, this is the orbital frequency actually, omega. They depend on the size of the moon, that's r, and then they depend on 2 terms that have a constant ratio. P20 is the flattening term. P22 is the football term. So the flattening term and the football term should have a constant ratio of 10/3. If you observe the ratio on the moon, it is 9. It is a factor of 3 too large. So the moon is either too flat or not football-y enough, whichever one you want. But regardless of which one is missing, the moon is able to maintain this shape, even though the shape it wants to be in has this 10/3 ratio. That means the strength of the moon's lithosphere is able to support itself against deforming back into the equilibrium shape, and it has been that way since very early in the history of the moon. Synchronization should have happened very quickly, less than 1 million years, most likely. So if we have such rapid synchronization, then the moon really should have adopted this shape, unless it was strong enough at the time it synchronized to resist that. Mercury also has an unusual shape. If we want to capture Mercury into its 3-to-2 spin orbit resonance, it needs to have an asymmetry prior to that point that the sun can use to torque it and capture it into the 3-to-2 resonance. Something, i.e. elastic forces, need to sustain that asymmetry, and the asymmetry has to be fairly large, or the sun will not be able to capture it into the 3-to-2 resonance. So this asymmetry must predate the capture, predate the tidal bulge that's produced by the resonance, and therefore must have been a very early feature. So again, Mercury is also sustaining somehow very large forces very early in its history. So all of these planets that we look at, except for Venus, and we'll get to that, have this ancient topography that has not relaxed. This, despite the fact that 5 to 8 times the heat that's coming through them now must have been going through them then. They should have had much thinner lithospheres. How are they able to support these loads? Well, this shouldn't be a surprise to most of you that rocks melt. And so there are limits to how hot you can make the interior of a planet before volcanism starts to take place. And that means there are limits to how much heat a planet can transport before it starts to melt. It can transport by the usual process of convection and then conduction through the lid. And that limit, that melting limit, changes the rules. When you are below that limit, we have the nice relationship between heat flow coming through the lid, convection going on underneath the lid. When we exceed that limit, we now have another way of transporting heat through volcanics. And so that erupting melt is bringing both heat and material up through the lid and bringing it straight to the surface, basically short-circuiting the lid. And so if we run 2 of those same fairly simple 2-dimensional simulations, one without melting, one with melting, both of them transporting exactly the same amount of heat, we find that when we enforce a solidus curve, that's what this line here is, we get a very different thermal structure in the lithosphere, and we get a somewhat different thermal structure in the deep interior of the planet. And what used to be transported, the heat that used to be transported by conduction along this rather steep geotherm, is now being transported by melt, which is produced here in this region and brought to the surface. Okay? And once we stop depending on conduction to do the heat transport, we can produce a much thicker lithosphere in the same, for a mantle that's transporting the exact same amount of heat. So we break that relationship between heat flow and lithospheric thickness. And this is how we can reconcile that early topography with early high heat flow. The melt, of course, works its way up through the lithosphere through a variety of processes that I sometimes refer to as magic, mostly because they're very difficult to study and understand. They depend a lot on the complexities of exactly how fluids work their way through brittle elastic solids. But regardless of how it happens, it happens. We see plenty of eruptive material on the surfaces of all of the terrestrial planets. And so melt will escape and take with it both the latent heat that it carries with it, as well as a significant amount of mass. And so we have both heat and material transport going through the lid. And that changes the behavior of the interior quite a bit. So this is a similar plot to the previous one. These 4 simulations without melting. Now we impose a solidus, and we see very significant changes both in the deep interior, but especially in the lids. And you see that the lids get thicker when we impose a solidus and we allow melt to transport heat. And so a few years ago, actually about 25 years ago, when studying Jupiter's moon Io, a couple of scientists, O'Reilly and Davies, christened this term heat pipes for the way that Io transports heat through volcanism. And we think this exact same process applies to all the terrestrial planets. So when we have this volcanism, extensive volcanism that comes up through these fairly narrow channels, and when I say fairly narrow, I just mean they're narrow relative to the thickness of the lithosphere. They bring heat up without losing too much heat conductively to the sides, and they deposit it at the surface. Even if there are losses along the way up, the interior will simply make more melt if it needs to in order to get the heat out. As that material spreads across the surface and cools, it pushes down the old surface. So you've got this kind of conveyor belt constantly moving old cold material downwards. Okay, that downward advection radically changes the temperature equation in the lid by adding this advection term to it. So the normal equation, normal diffusion equation for temperature would just have a heat source. If you've got internal heating, you've got the diffusion part of the diffusion equation, but now we've got to add the advection part. This is the new solution to that equation when you include the advection part. And there is a critical parameter here, lambda, which is the ratio of the advective velocity v to the diffusive velocity or the conductive velocity, which is just d over kappa, or I've written this out as d divided by, or d times rho c sub p divided by k. A typical conductive velocity for a 30-kilometer thick lithosphere is about 1 millimeter per year. So if you are supplying enough melt to bury the surface at about 1 millimeter per year, then you're beginning to see some pretty strong effects due to this advective term. And here are some solutions of that equation for different values of lambda. So here's that lambda equals 1 term. So that would be where the advective velocity is equal to that diffusive velocity. Using that scaling I just gave, this would be about 1 millimeter per year. This would be about 3 millimeters per year, and that would be about 1 centimeter per year in terms of burial rates. And here at lambda 0.1, this is basically your standard conduction solution where the advection term doesn't matter too much. What you should notice is that as that advection term gets stronger and stronger, the lithosphere gets colder and colder. And because we're basically taking that surface boundary condition and we're pushing it down into the lithosphere. So not only are we generating thick lithospheres, we're generating cold lithospheres. So these thick, cold, strong lithospheres are produced by this heat pipe mechanism. Whoops. And so this heat pipe mode of heat transport happens when the volcanic heat transport dominates the conductive heat transport. And there is actually one place where that's happening right now. Jupiter's moon, Io, as I mentioned, has volcanoes. And you can see this is a very short animation. It's only 3 frames as the New Horizons spacecraft zoomed through the Jupiter system on its way to Pluto. But it took these beautiful 3 frames that included this really nice plume of sulfur volatiles blasting off the surface of Io and then falling back down. The reason these things are exploding off the surface is that there is a silicate lava flow spreading out across the surface of Io. All of these black features are examples of that. When the Galileo spacecraft was in orbit around Jupiter, it took a picture of Io while Io was in Jupiter eclipse. So Io is completely in shadow, and took an infrared image. And every one of these bright dots is an active volcano. Okay, so Io is very active. Here's a nice close-up. You can actually see some of these sulfur compound vents sort of blowing away from what is basically a large lava lake with a fair amount of crust on it in some places and some more open spots around it. So Io is the most volcanically active body in the solar system, and I really should try to collect my nickel for every time people say this, and then I can retire. Its current heat flow is 2.5 watts per meter squared. Okay, that is 40 times the Earth's heat flow on a per meter squared basis. It's 100 terawatts. Just to remind folks, Io is about the size of our moon. And so something the size of our moon is generating 100 terawatts of heat flow. That's an awful lot of heat. We have been able to measure the temperatures of certain individual flows. They are very hot. We have not observed a single impact crater on the surface of Io. That means its surface is getting covered quite rapidly. And the heat source is tidal dissipation from the huge tides raised by Jupiter as Io goes around. But at the same time that Io has all of this volcanism and all of these volcanic features, it also has what are quite clearly tectonically bounded mountains. These are big blocks of rock getting shoved up into the sky, some of them over 20 kilometers high. So if Io is pumping 2.5 watts per meter squared through its lithosphere, how is it supporting a 20-kilometer tall mountain? The equilibrium lithospheric thickness is about 2.5 kilometers if you allow it to go through by conduction. There's no way to stack a 20-kilometer mountain on a 2-kilometer thick lithosphere. So how does EO manage to do this? This is heat pipe in action. So that 2.5 watts per meter squared nonetheless, or actually produces, because of that volcanic conveyor belt, a thick and strong lithosphere that's able to support those 20-kilometer mountains. Okay, let's apply this to the other planets. So if we look at the time evolution of a heat pipe planet, it begins with a very thick and strong lithosphere. That's this red line. If we compare that to a planet with no melting that is forced to remove heat by conduction, it has to start with a rather thin lithosphere. Over time, as the heat-producing elements decay, that thin lithosphere can gradually thicken. But in the heat pipe case, we have a thick lithosphere that actually gradually thins until at some point the heat transport by the mantle ceases to require temperatures above the melting point, and now we can basically join the same evolution as we have for the non-melting mantle. So you can see that in a heat pipe planet, the history of the lithosphere is extremely different than the history of the lithosphere in a planet that does not experience heat pipes. Rather than continuously getting thicker and thicker and thicker, it actually starts extremely thick, goes through a period of thinning, and then begins to thicken again. In addition to building this strong, thick lithosphere, heat pipes also reduce the stresses on the lithosphere. This is because they are literally sucking buoyancy out of the boundary layer at the top of the mantle and bringing it to the surface. All that hot lava is buoyancy that was piling up at the bottom of the lithosphere. And so on the right here, we have the stresses. This is an example of a calculation during the heat pipe mode. Here's the temperature field. Here's the stress field. You can see that the stresses are rather low, particularly up here in the lithosphere. We have quite low, several regions of quite low stress. And then over time, as the heat production decays, heat pipe stops operating. We go back to kind of normal convection, and we start generating much larger stresses. And in this case, we eventually generate enough stress to actually break the lithosphere and initiate a subduction-like event. Okay? I won't call this an actual subduction event, but we have a subduction-like event. And so in that particular model, and in the models I'm showing here, we have a transition from heat pipes with thick, strong lithospheres and weak mantle stresses to a gradually thinning lithosphere, and then eventually a lithosphere that breaks. And we're referring to that as a plate tectonic transition. So over here, this black line is the decay of the internal heat sources. These squiggly lines are the volcanic heat transport, and these lines are the conductive heat transport. And you can see that over time, the volcanic heat transport gradually decreases over time until there becomes a point at which we transition from volcanically dominated to conductively dominated. Eventually, the volcanism gets down to near zero, and roughly around the time that it does that, we begin to develop stresses that are big enough to break those plates. So in this particular set of models published by my student Duminda Kankanangi a few years ago, we see a distinct transition from heat pipe behavior to a period that you might call rigid lid behavior, and then that lid breaks. If we look at the stresses over time, they begin as the internal heating rate decays, they begin very high, the stresses decrease, and then they go back up as we approach that plate tectonic transition. The Earth, for example, would have started somewhere in here, experienced a gradually increasing set of stresses until we eventually broke the plates and initiated plate tectonics. EO is somewhere over here on this end of the diagram. So what controls this transition from heat pipes to convective behavior? It has to do with the ability of convection to keep up with the heat production. that is convection below the solidus. So this is a graph showing the internal temperature and the heat flux as a function of internal temperature. So this is how much heat convection is able to accommodate at a particular temperature. As it warms up, the viscosity decreases, convection gets more and more efficient, it's more able to remove heat. When we hit the solidus, convection gets a lot better at removing heat because liquid actually really decreases the viscosity. But, whoops, sorry, let me back up. So this is sort of a standard behavior of convection. As the viscosity decreases, convection gets more efficient at removing heat. If we increase the gravity, if we increase the delta T across the planet, if we lower the viscosity, we take this whole curve and we slide it upwards. The interior just becomes better at removing heat. So at any particular temperature, it's able to remove more heat. So if we're comparing two planets, we may see one with a low gravity or a low delta T or a high viscosity here, and one with a higher gravity or higher or lower delta T up here, or higher delta T up here. When we think about how planets evolve along this graph, they start over here at high temperature and high heat flux, and they work their way gradually as they cool, and as the heat fluxes decay, they work their way from upper right to lower left on this diagram. Up in this regime, we have volcanically dominated. We're above the solidus. We have heat pipe behavior. Eventually, we get to the point where we cross the solidus and we can move on to more standard convection behavior. Notice if a planet is more efficient at convection, that is, it has a larger gravity or a larger delta T, then we can transition earlier. We can transition at a higher heat flux and a higher temperature than if the planet is less efficient. So when the planet is more efficient, convection takes over earlier. When it's less efficient, convection has to wait until the heat sources decay low enough for convection to keep up. This is the results of a set of simulations I did with another student, Debajyoti Basu Sarkar, where we looked at let's look at the red dots and the red scale here. We looked at the internal heating rate at the time that conduction basically took over. So that's when conduction is equal to the internal heating rate. That's the point at which heat pipes stop, essentially. And if we change, for example, the surface temperature on each of these simulations, we find that simulations with a high delta T, that is a low surface temperature, a cold surface, they transition at a higher internal heating rate. In other words, they transition earlier. That's the blue dots. Whereas if we have a high surface temperature, which reduces the efficiency of convection, we transition at a lower internal heating rate. In other words, we had to wait. If you compare these two, by the time the surface temperature is 0.5, that means we have reduced delta T by about a factor of 2. And so in that particular case, we have reduced that conductive internal heating rate also by about a factor of 2. Okay, so we just had to wait one half-life for this transition to happen. If we look at Venus, Venus's surface temperature causes the delta T to be not quite half of what it is on the Earth, a little bit more than half. It has a slightly lower gravity. It has a slightly smaller radius. So all of those things combined make Venus about 50% as good at transporting heat as the Earth. And so that means if Venus wants to transport all of the internally generated heat, it has to wait a half-life later than the Earth does. The half-life of those heat-producing elements in Venus and Earth are about 1.5 billion years. If we look at various lines of geological evidence for when plate tectonics started on the Earth, it's around 3 billion years ago. So if Venus has to wait another 1.5 billion years after that, then Venus was actively in the heat pipe regime until about 1.5 billion years ago. If we look at the surface of Venus, we find craters all over the place and an average surface age of between 750 million and 1 billion years. That is very similar to around the time that Venus would have transitioned out of heat pipes. So there is also very little variation in the crater preservation across the surface. That is, pretty much every part of Venus looks like it's the same age. There are some very slight variations, but not too many, and they're really hard to pick out because there aren't all that many craters. So this suggests that whatever transition happened, it was global. So is Venus a recent convert from heat pipes? I mentioned the broadly resurfaced until about 0.75 to 1 billion years ago. It has a very thick lid with large variations. We get that from the gravity and the topography. We see areas of regional extension. Remember that the heat pipe planet actually goes through a period where the lithosphere gets thinner. During that period, you're going to get tension in the lithosphere. And that may be what's responsible for these large rifting regions. You can see sort of all of this area. These are all rifts that connect the large volcanic provinces. So Venus may be an example of a planet that more recently converted out of the heat pipe mode. And that's what I was just saying about, just to remind you that a heat pipe planet actually goes through a fairly long period of lithospheric thinning as it transitions out of heat pipe. And that might be what's responsible for that extension. Oh yeah, here's the slide about that. So I often get ahead of myself. So here's a nice example of rifting on Venus. Here's a crater. Here's the other half of that crater. And you can see that if we were to connect the circle, this part of the crater has been pulled apart by quite a bit. And we see a lot of these features, but this is a very nicely marked one on the surface of Venus. Another thing that in addition to reducing the buoyancy and the stresses on the lithosphere, heat pipes also eliminate plumes, because mantle plumes come from cold material being delivered to the core mantle boundary. Well, in this case, we keep sucking the buoyancy out of the top, and that means there isn't a whole lot of cold material being delivered to the lower boundary. So we don't generate much in the way of plumes during the heat pipe era. Once heat pipe ends, then we can start generating some plumes, and those plumes will help that transition, the lithosphere transition from this thick state to the much thinner state later on. Okay, so for the Earth, we started at a high heat flux. We gradually moved lower and lower until we got to a point where, thanks to the fact that we had these strong buoyancy forces, we were able to break the plate and move into the plate tectonic regime. If we reduce the efficiency of heat transport, we close that window. It is harder to break the plate when you have to wait until there's only half as much heat source, because that's the source of the energy for breaking the plates. So if I don't transition into convection until a whole half-life later, I've got half of the energy I needed to break the plates. And here is Venus with less buoyancy forces, weaker gravity, weaker delta T, forced to wait until the heat sources decay to the point where we are no longer able to break the lid, and we transition straight into single plate behavior. And so the punchline of this, here we go, is that Earth and Venus, despite being very similar, nonetheless have really different convective efficiencies. They're different by a factor of 2. And it's mostly due to the surface temperature effect. So if Venus had the same atmosphere as the Earth, we might have expected it to transition into plate tectonics because its convective efficiency would have been fairly similar to the Earth. But because it has this thick blanket of CO2, keeping the surface temperature high, that interior convection is not very efficient. It has to wait a whole extra half-life until it can transition, and it transitions late at a low stress state and fails to get into plate tectonics. The Earth at some point will run out of steam and transition down to rigid lid itself, but it's got a little ways to go on that. Okay, so this is just a brief wrap-up. The ability of planets to transport heat by heat pipes suppresses plate tectonics. With a low delta T and a somewhat lower G, Venus transitions later at a lower heat flow. Venus actually also has a somewhat lower solidus slope, that because it's slightly smaller, that also extends the heat pipe era. And so the moral of the story is Venus wasted her youth on heat pipes and missed the plate tectonic boat.